Okay, so here we're going to find the electric field and the electric potential due to a long uniform line charge. And we're going to do it two different ways. First, we're going to use Gauss's law to find the electric field and then integrate in order to get the electric potential. And then the other way, we'll just find the electric potential directly by adding up the contributions from all the little pieces of charge. So first, let's use Gauss's law. Gauss says that the integral of E dot dA is Q enclosed over epsilon naught. We have a charge per unit length lambda and a total length of L, so the total charge is lambda L so long as I enclose all of it. And the thing is, what should you enclose a cylindrical looking object with in Gauss's law in order to exploit the symmetry? A cylinder. You basically pick the exact same shape that you're enclosing, because if you do this, the cylinder has the exact same kind of symmetry as your charge does. And what that means is that this integral is not an integral at all. You can make the argument that because of cylindrical symmetry, the electric field has to have the same value everywhere on that cylindrical surface. And so this integral is not really an integral at all. Here's another way to see it just by looking at a cross section of it. At any given radius, the electric field looks the same. So if you integrate over the surface, the E field is constant and it just becomes E times A. The area of a cylinder is 2 pi r times L. Okay, so the left hand, the integral, just becomes EA. So that's EA, that equals lambda L over epsilon naught. And beautiful, we've gotten the electric field using Gauss's law. So now the question is, how do you find the potential between 2 points? So a point that is R away and a point that is, let's say, A away. Okay, well, you integrate from R to A of minus E dot dr. We know what the electric field is, and so we're looking at the potential difference between some point A and some other point R. And if we do that and we integrate, you end up with this. So voila, here is the potential of a cylinder. Notice that I don't have the potential of the cylinder relative to infinity. I have the potential at R relative to A. And the reason for that is if I make this cylinder extremely long, like when we say long, what we really mean is infinitely long. The problem is that the potential does not go to zero at infinity because there's charge at infinity. You can't get infinitely far away from the charge. And so when you have situations like this, you end up always having to take the potential between two specific places. And for us, I just said some random place, the point A, and we'll reference everything against that. So any distance R is referenced against this point A, which is farther away. Okay, so that's that. That's how you find it using Gauss's law. Now the question is, can you skip finding the electric field and just get the potential directly? Of course you can. If you have a point charge, then the potential difference between that point charge at a point R and A, this is just basically Coulomb's law for charge. So our technique is we pick one little tiny piece of this thing that has a charge, dq, and then we look some distance R away, right? And this looks something like X and R. And if we were curious about the point A, well, then you basically get the same thing, except now it's R squared and A squared. And our job is, first we find the contribution due to this piece of charge. That's this. And then we draw a piece of charge next to it, and we find the contribution due to that charge. And again, and again. And basically, we're going to do an integral. And the thing that's going to change is X. This line gets farther and farther away. Okay? So the integral we have to set up is this one. We go from minus L over 2 to L over 2. In other words, let's start at the midpoint. We'll go from minus L over 2 to L over 2, and we will integrate up all the little contributions. And so it's ugly, but this is essentially what it looks like, and this is the potential difference between the point R and the point A. If you do this integral, you end up with this ugly, gross, disgusting looking thing. And this is the electric potential. I promise this is what the integral gives out. You can use, whatever online integrator you want, or if you're hardcore, do it by hand. They don't look anything alike, but I said very long, very long. If you take the limit of this function as L approaches infinity, I swear on my children's lives, you'll end up with this. One thing I'll just tell you, if you want to work that out for yourself, something you need to exploit is that 1 plus x to the n is roughly equal to 1 plus nx. 1 plus nx. And I've used that trick here. And if you want to work it out, you'll need to take advantage of that. Here, the n is 1/2 because we're taking square roots. Okay. Anyway, you might say, oh, it's always better to compute the voltage, the potential difference directly using this. I don't know. This is pretty ugly. In this case, for me, I think it's faster to just use Gauss's law. But there are other situations where this will be faster. The takeaway from this is that you need to have both tools. And if you have both tools, you can do it either way. Okay, feel free to ask questions if you have them.